Okay, good evening, everybody. Welcome to another episode of Cosmos from Your Couch. My name is Michael Reed, and I'm a professor at the Dunlap Institute for Astronomy and Astrophysics at the University of Toronto, and I'll be your host this evening. Tonight's guest is Dr. Patrick Breysse, who will be talking to us about the origins and basic early beginnings of the universe. But before we get to that, just a couple of notes about how this will go. So Dr. Breysse will be taking questions, but he'll be taking those at the end of his talk. So if you have questions, please feel free to share them in the chat on YouTube as we go along. But we'll compile those and I'll pass those along to him at the end. But do please feel free to share them as they arise for you so that you remember. And then at the end, I'll tell you a little bit more about our next upcoming Cosmos from Your Couch talk. So as I said, tonight's guest is Dr. Patrick Breysse. Dr. Breysse is a postdoctoral fellow at the Canadian Institute for Theoretical Astrophysics at the University of Toronto, where he studies things related to what he's going to tell you about today. Cosmology, the study of the universe on the largest scales of time and space, the origin and the end of things. Tonight he's going to talk about cosmic dawn, and I'll let him describe to you a little bit more about what that means. If you enjoy tonight's talk, please be aware that Dr. Breysse gave a previous talk in this series, which I've linked in the video description below, and that was called A Brief History of Everything, which was really a wonderful talk. So please check that out after we hear from Dr. Breysse tonight. So without further ado, here is Dr. Patrick Breysse.
All right. Thank you very much, Mike, for the lovely introduction. Like Mike said, my name's Patrick. I work at the Canadian Institute for Theoretical Astrophysics at the University of Toronto. And I am here tonight to entertain you through our continued pandemic slowdowns by telling you all about a kind of one of the final unexplored frontiers in cosmic history, and one of the most important periods in cosmic history, a time called cosmic dawn, which, the Big Bang was when the universe was born, but cosmic dawn is the time when the universe really became the way we see it today. It's really the time when the universe lit up. And so I'm going to talk about what cosmic dawn is, how much we don't know about it, and I'm going to talk about some of the really exciting kind of fundamentally new ways of doing astronomy we're developing to try and see cosmic dawn happening for the first time. So I hope you enjoy it. Okay, so if you go out at night, look up into the sky, almost every point of light you see in the sky is a star. If you're, in a really good dark place, you'll see hundreds and hundreds of them, too many to count. If you, like me, live in the middle of downtown in a major city, you might be able to see the handful of brightest stars. But it's unquestionable that the view we see at night is dominated by stars of all shapes and colors. Even, the bright band of the Milky Way, which just kind of looks like a cloud, is actually made up of thousands and millions of stars that are so close together you can't tell them apart. There are a few points of light in the sky that aren't stars. Anybody who's spent time looking out at night will recognize the moon, obviously. And some of the brighter dots you might see in the sky will often be planets. In our own solar system. In this particular picture, we can see Mars, Saturn, and Jupiter lined up very photogenically for us. But even the planets we see, they don't really shine on their own. The light from these planets still ultimately comes from stars. In fact, in this case, it's the light of our nearest star, the sun, reflecting off these planets and shining back into our eyes. The stars are really fundamental to our understanding of space. They're almost synonymous in our heads when we talk about space. If we're telling a story about people having a big fight in space, what do we call it? We call it Star Wars. If people are going on journeys and adventures through space, we call it Star Trek. To the average person, space and the stars are basically the same thing. And even more so than that, our nearest star, the sun is what gives us the light we use to see by. The energy from the sun is what fuels the food we eat. And the heat from the sun provides the warmth that keeps us from freezing to death, even when some of us decided to live in Canada for some reason. So, life on Earth and our entire concept of the universe is almost entirely revolves around stars. So it might sound very strange to think about a time in the history of the universe where there weren't any stars. For a long time at the beginning of the universe, there were no stars. There was basically no light of any kind. The universe was just empty blackness as far as you could see, except you can't see anything, both because you don't exist and because it's empty blackness. And the universe was like this for the first 300 million years. For context, it's only been 65 million years since the dinosaurs were wiped out. So it's a very long time with no light whatsoever. The cosmos would be completely unrecognizable to a hypothetical time-traveling human. And this period of darkness came to an end rather suddenly after about 300 million years in an event called cosmic dawn. And what cosmic dawn is it's when the very first stars in the universe were born. And the light from these stars spread out into the universe and kind of reshaped it in their own image, transforming the universe kind of a fog of pitch black hydrogen to the familiar star-studded landscape we see today. And so what I'm going to talk about today is how this cosmic dawn happened and how we're trying to see it. Because, this is a kind of super important event in the history of the universe. And it's one of the last ones that we have basically just not been able to see at all. So to start off, before I went to get into the big, exciting topics about the first stars being born and, let there be light and all such good things, we got to start at a little more basics. Going to ask the question, what is a star? Because, saying there are little dots of light in the sky is one thing, but if you want to know how the first stars were born, then we need to know a little bit about what stars are. And to learn about what stars are, unfortunately, we have to talk a little bit about chemistry, which was one of my favorite subjects in college. Not really. And I'm sure a lot of other people have similarly favorable memories of this complicated looking grid of messy symbols that, maybe we barely understand. The good news for when astronomers start talking about chemistry is we really don't care about most of this. To an astronomer, the periodic table of the elements basically consists of hydrogen, which is the lightest element, makes up most of the universe, helium, which is the next lightest element and the one that makes your voice sound funny when you breathe it, and all the rest of it we group in the category of metals. This is because we are altogether too lazy to give all of these things different names. I don't care if it's, oxygen gas or carbon or, liquid mercury. It doesn't matter. It's all metals. And the reason why we can get away with, ignoring most of the stuff in this table is that if you look at what the matter in the universe is made of, it's about 3/4 hydrogen, about 1/4 helium, and the rest of this stuff in the periodic table adds up to a total about 2% of the stuff in the universe. So for the vast majority of time, when you're thinking about space and trying to figure out how something in space works, you can basically pretend it's made of entirely hydrogen and helium. And even a lot of the times you can pretend it's just made of hydrogen because that's still 3/4 of the stuff. So if we want to understand, how stars work, then really we have to think a lot about hydrogen. I'm going to talk a lot about hydrogen tonight. I hope you're ready. So hydrogen atoms, if I got a couple of hydrogen atoms floating out there in space, for the most part, they're not super friendly. If I, take 2 hydrogen atoms and bring them close together, most of the time they'll bounce off and run away from each other. And that's because the hydrogen atoms, the nuclei are both protons and they have the same charge. So when you bring them close together, they say, "Nuh-uh, I don't like you," and they run away as fast as they can. However, if you can take those hydrogen atoms and forcibly squeeze them together, you have to push really hard, but eventually they'll decide, oh, turns out we're actually best of friends, and they'll squish together and make a helium atom. It's kind of like protagonists in a romantic comedy where, the guy and the girl hate each other at the beginning, but then they go through some, crazy adventure, and by the end of it, turns out they were in love the whole time. Now, there's something very special that happens when you fuse hydrogen atoms together to make helium. And that is, if you were to take the hydrogen atoms you started with and the helium atom you end up with, and you weigh them, the helium atom weighs a little bit less than the stuff that went into it. It's a little bit like somebody asking, what's 1 + 1? And you say 2, and they say, no, what are you talking about? It's not 2, it's actually 1.9. That's really weird, right? Some of the stuff that was in those hydrogen atoms is somehow gone. And where that goes ends up being pretty much fundamental to our ability to exist at all. And the reason for that comes down to this guy, dignified, famous physicist that he is, and the single physics equation that most people who don't work in the subject actually know, the famous E equals mc squared. Now, to translate that from algebra to plain English, E equals mc squared translates to energy equals mass times what we in the technical field call a really frickin' big number. And that really big number means that this, itty bitty mass difference between the hydrogen atoms I started with and the helium atom they turned into, you take that itty bitty mass difference, you multiply it by that really big number, and you release a huge amount of energy. How huge are we talking? Well, on Earth, we figured out how to fuse hydrogen atoms into helium. And pretty much the only practical use we found for it so far is to make really big bombs, because that amount of energy release turns out to be really perfect for vaporizing things you decide you don't want to have exist anymore. So what does all of this have to do with that question I asked at the beginning? What is a star? Well, it turns out a star is basically just a big nuclear bomb. If you look at a star, stars are enormous. They're millions of times bigger than, say, the planet we live on. But if you look way down deep in the star, right in the very center, in the hottest, densest part, the weight of all of that mass of incandescent gas, because apparently that's a song that's stuck in my head now, is enough to squeeze the hydrogen atoms in the core together and fuse them into helium, releasing that energy. And that energy that comes from that itty bitty mass difference is what makes the star shine. That energy is what comes out of the star and streams through space and keeps us alive. And it's what makes the rest of the star kind of boil and flare, because there's basically a continuous nuclear bomb going off in the center of it. Now, the mass difference between, hydrogen atoms and a helium atom is a lot by atom standards, but not that much on human scales. These are still atoms we're talking about. But when you're talking about the sun, the amount of mass the sun is losing every second, the amount of matter that is just being annihilated and turned into sunlight, is about 4 million tons every second. Now, 4 million tons is starting to get into one of those astronomy numbers that's kind of too big to actually mean anything to you. So to put it in a little bit of context, that's a little less than a Great Pyramid every second. That's just gone from the universe and turned into the light we use to see, the light we use to feed our crops, and the heat we use to not freeze. And so a star is basically a giant nuclear reactor that is constantly running this nuclear fusion reaction, constantly turning its own mass into light. And the process doesn't stop with hydrogen and helium. Eventually, helium atoms, as the star grows, as it starts to run out of hydrogen in its core, it'll start to turn helium into all of those other metals that, I said for the purposes of our math, we don't usually care about. And this is important because as much as astronomers like to ignore the rest of the periodic table, on Earth, the air we breathe and the water we drink's got to have oxygen in it. Our bodies ourselves are primarily made of carbon. Our atmosphere that keeps us from freezing to death is mostly nitrogen. And even heavier things, sorry, computer dying. Even heavier things like iron. I am sitting in downtown Toronto and basically everything around me that I can see is iron. And these elements are made in the nuclear furnaces at the centers of stars. So not only does our nearby star keep us alive, but past stars actually created the very elements we're made of. Now, if we look at nearby stars in the universe, like I said, by mass, these stars are about 2% or so made of metals, made of everything that's not hydrogen and helium. Now, this is true for nearby fairly young stars. But as astronomers got better at doing astronomy and started looking further and further out into space, they found that there was another kind of older looking stars. And these stars had much less metals in them. They were even more completely dominated by hydrogen or helium. And what people figured out from this is that since we know that heavy elements, that metals are made inside the nuclear bombs going off inside of stars, then it seems likely that these older stars we see with their less metals are kind of the parents of the stars we see around us and the star our planet is orbiting. So if we have, a stick figure family of stars, we'd have these older low metallicity is the term we use for this, stars, dying and filling space with the elements that then go into making younger stars and planets and, eventually giant ridiculous cities. Now, one of the themes of this talk is going to be that astronomers are kind of terrible at naming things. So when we try to name these different groups of stars, well, we discovered these nearby stars first, and we didn't initially know that these were actually the younger stars. So we decided we were going to call the nearby younger stars population 1 and the older stars population 2, which of course makes absolutely no sense because population 2 comes before population 1. But the problem gets a little worse, because from our study of the beginning of the universe, we know that the Big Bang, when the universe was created, couldn't even make this tiny little bit of metals that show up in the older population 2 stars. And what that means is there must have been some grandparent stars in our stick figure family. There must have been a previous generation of stars that made even the metals that we needed to have in the population 2 stars. Now, people, once we figured that out, then thought about, okay, what is the kind of least intuitive, most annoying name we could possibly give to these stars? Well, we'll call them population 3, because of course that makes sense given that they're older than everything else we see. And it's these population 3 stars that first formed in cosmic dawn from the raw primordial gas of the universe and lit it up for the first time. So at the time these stars were formed, like I said at the beginning, the universe was basically pitch blackness. Not empty blackness. There was still a lot of hydrogen gas floating around, because there's basically always a lot of hydrogen gas floating around, but no starlight to see by, nothing we would recognize as, like a Hubble Space Telescope picture or something. Continuing the theme of being terrible at names, astronomers have named this period of cosmic history the Dark Ages, because it's an age that's dark. But now, during this time, if you, were to time travel back and sit there, you wouldn't really be able to see anything happening. But it turns out that these clouds of hydrogen gas are steadily collapsing under their own gravity. If you want to hear more about this process, you can listen to my other talk, which is basically all about stuff collapsing under its own gravity. And so what we're seeing here is a computer simulation of the gas in the early universe, where the bluer regions are places where more and more of this hydrogen gas is starting to pull it together. And as we watch, as time passes, you start to see, suddenly you see lights appear amidst what to us would be invisible gas. And these are these population 3 stars showing up in the midst of this empty universe and bringing light to it for the first time since the Big Bang. Now, these stars are not like the stars we're used to seeing today. Our sun, for example, is a pretty medium-sized star as these things go. There are stars bigger than it, there are stars smaller than it. It's kind of more or less in the middle. Honestly, kind of unremarkable as these things go. Population 3 stars, though, the stars that were burned during cosmic dawn, they are a little bit bigger. I'm talking like hundreds to thousands, hundreds of times more massive than the sun, dramatically larger in radius, and way, way brighter than the stars we see around us today. And this is because they formed in this kind of pure hydrogen and helium gas at the beginning of the universe. If you add even like 2% of metals to your mix, it kind of messes up the process of the gas collapsing into stars a little bit. It tends to make it want to collapse more into a bunch of small stars rather than a few really big stars. And so these population 3 stars, without any of that contaminant hanging around, we think, we don't know, because like I said, we haven't seen cosmic dawn yet, we think are going to be very, very large. And this has a consequence for those stars. And the fact is that the bigger a star is, the more light it's giving off, the faster it's going to run out of energy from that nuclear bomb going off in its core, and the faster it's going to die. So if we watch this video again and let it keep playing, we see that, it takes hundreds of millions of years. The beginning of this video to where little dots start showing up is a few 100 million years, depending on exactly how you run your theory. But if you watch these newborn stars, you'll pretty clearly see them start to disappear in giant explosions we call supernovae. So these stars, they're the product of hundreds of millions of years of gas patiently collapsing together in the darkness. And yet they themselves only live for, probably only like 10 million years or so. Now, 10 million years ago is a lot by the standards of humans, but compared to the scale of the universe, 10 million years really isn't that long. But in their brief lives, these stars will create the elements that eventually seed planets like ours, and they will, in their limited lifetime, reshape the universe in their own image. And that process is due to a magic of a process that we call reionization, or maybe spelled with an S if you're British, and maybe spelled somewhat ambiguously between them if you're Canadian, because Canadians can't make up their mind about whether they're using British stuff or American things. So what this reionization process is it's another fun little property of hydrogen atoms. So a hydrogen atom floating in space by itself in its kind of basic neutral state consists of a positively charged proton being happily orbited by a tiny little electron. And normally, hydrogen atoms, two hydrogen atoms will repel each other because they have the same charge. But the proton and the electron have opposite charges, so they're very tightly stuck together. They are best of friends. And they will stay together basically forever, unless, say, you put a giant freaking star right next to them and shine a really bright light on them. The energy from that light is enough to blast the electron right off of the hydrogen atom. And when you take this, cloud of previously undisturbed gas that's basically filling the entire universe, and suddenly plonk a bunch of really bright stars into the middle of it, well, these stars start to blow giant bubbles of ionized hydrogen in the gas, of bubbles where all of the electrons have been blasted off their hydrogen atoms. And so what this video is showing is a computer simulation done by a former member of the institute I work for. The black spaces are places where hydrogen and its electrons are still friends. They haven't been close enough to the stars. Whereas the blue spaces are these bubbles that are being blown, where the electrons have been burned off of their hydrogen. Now, note that this is not saying that the universe is a cube. This is a computer simulation that just happened to make a cube because cubes are easy. That as we watch, eventually the light from these stars burns off all of that neutral hydrogen gas, blasts off basically all of the electrons in the universe, to the point where almost every hydrogen atom in the universe today is ionized. And by the end of it, we are left with the familiar starry sky full of galaxies we see today. This reionization process is the last great phase transition of the universe. Now, obviously, what's the fun of going to an astronomy talk if you don't learn some fancy words that you can say to your friends to sound smart? A phase transition is, normally on Earth, we're used to talking about phase transitions like when ice melts into water or when water boils into steam. But in cosmology, when we talk about a phase transition, we're talking about a time when the entire universe changes at once, on a very short time scale. So, we had phase transitions like back during the Big Bang when, the universe itself was formed, or when atoms were formed for the first time. But this cosmic dawn event is the last one of these phase transitions, and it's what really sets in motion the universe as we see it today. So if we look at our history of the universe, here, this is a timeline where with the Big Bang, the beginning of the universe on the left, and our modern day universe on the right. We start with the Big Bang, which throws the universe into motion, sets the whole of space and time expanding. And then very quickly, the light and heat from that explosion fades out of the visible, and we enter this few hundred million year dark age period, which is then abruptly ended by the formation of the first stars and the first galaxies in cosmic dawn. These stars reionize the universe and burn off that hydrogen fog, and eventually those stars and galaxies and the metals they create grow to form the planets and stars we see around us and in fact live on today. Now, you might notice that throughout this discussion of what cosmic dawn is, I didn't actually show you any pictures of anything. I didn't show you any pictures of any population 3 stars or early galaxies or anything. You know, normally astronomers love to put pictures from various telescopes in their talks. And that's because, you know, we know this has to have happened at some point. We have some really good theories that describe more or less how it happened, which is why we're able to show these really nice computer simulations of how the process went. But we can't actually see it yet. Now, you might say, of course you can't see it. It happened billions of years ago. You couldn't see that unless you were, you know, had a time machine of some kind. Well, it turns out that's not actually the problem. And that's because astronomers actually do have time machines. We call them telescopes. This is something else I talk a little bit more in the other talk that's linked in the description. But basically, since light travels at a finite speed, it takes light. Light doesn't get from one place to another instantaneously. Whenever we're looking at something, we are looking at it a little bit back in time. So for example, the moon, it takes light about a second to get from the moon to Earth. So when we look at the moon, we're looking about a second back in time. This means when we're looking at something billions and billions and billions of miles away, we're looking a very long time, very far back in time. So in principle, I should just be able to go outside with my telescope, and this is actually a picture of me with my telescope, point it out into space, look as far away as I can see, and I should be able to see these. And you know, if I see something far enough away, I will know that that is one of these first stars being born. I would, in principle, be able to see cosmic dawn as it's happening. However, I can't do that, and this is for very highly technical reasons that I really want to make sure, you know, I might have to talk about a little bit to make sure people understand. So far away stuff is hard to see. So it's not just a matter of looking beyond stuff. We actually have to work really hard to try and see these far away things because they're very faint, they're very small. We have to work really hard. And this is something a lot of people are working on because we really want to see these first stars for ourselves. So how do we actually try to do this? Well, the first thing you could do, I said, obviously me and my little backyard telescope aren't going to work, but what if we use a really nice telescope? So for a little while now, just about the nicest telescope we've had as humanity, it's been the Hubble Space Telescope, which has been orbiting around about 100 miles up there for, you know, a few decades now. And because this telescope is in space, away from the Earth's atmosphere and the annoying distortions that creates, Hubble telescope can see very clearly and can see very far away. So recently, a couple years back, some astronomers used Hubble to look at a tiny patch of sky near the Big Dipper. And because this is a very nice telescope, they were able to zoom very, very far in, looking past all of the nearby stars, which is most of what you're seeing now, looking past even all of the nearer by galaxies in the universe. And they found this really tiny, almost indistinguishable red smooge, which they were able to blow up, and this is the best picture they could get of it. When they took a picture of this little smudge, sorry, I want to get it back. When they took a picture of this smudge and measured how far away it is, they figured out that this is actually the farthest away galaxy we've seen. And when you're looking at galaxies through a telescope like Hubble, what you're really seeing is the light from all of the stars in that galaxy. So we are seeing some of the oldest stars in the universe in this picture. Now, it's not quite enough to get all the way back to cosmic dawn here. You know, we haven't quite gotten that far, but it's pretty close. This is during kind of the period where those stars are ionizing the universe. This is some of the earliest stars, if not the very first ones. And hopefully in the next year, since it was just announced that it's being delayed again, thank you, pandemic, we'll see the launch of Hubble's replacement, the James Webb Space Telescope, which is this kind of Death Star looking thing, which is just basically a bigger and better telescope than Hubble in every way. And with this telescope, we might just be able to push back far enough to see the very first stars in the very first galaxies. It's going to take a lot of work. We're going to have to stare at the same bit of sky for a very long time, but we might just be able to do it. So that's the easiest thing to do, just build a fancy telescope. But even James Webb, that's an $8 billion telescope. That's a lot of work. And we're still not sure we're going to be able to see these things. And if we do see them, they're going to be these kind of indistinguishable little smooches in our telescope. So what else can we do? Well, we don't have to just build our own telescopes. We can try to use the entire universe as a telescope. Now, what do I mean by that? Well, when we build a telescope, obviously things that cost $8 billion that we're putting to space are quite complicated. But what a telescope really boils down to is using a mirror or a lens to collect light from as big of an area as we can and squish it all down into our eyes or a camera. And since we have, a mirror that's much bigger than our eyes, we can collect much more light than our eye can see and see much fainter things. That is basically the entire purpose of a telescope. So people spend their time building bigger and bigger telescopes to try and collect more and more light. That's half the reason why James Webb is going to be better than Hubble, is because the mirror is about 3 times bigger. So what we can do, looking out into space, is we can use gravity to do the same thing. So if I have a really massive galaxy floating out in space, the gravity of that galaxy will actually bend the light coming from behind it. This is a consequence of Einstein's theory of relativity, and actually the first real evidence that it was the right way of thinking about things. And just like the mirrors in our telescope, we can use that to see galaxies that take a faint galaxy that's behind this massive lens and bend the light from this galaxy towards us, making it appear much bigger and brighter than it actually is, and enable us to see farther than we're able to by ourselves. Since this process involves using gravity as a lens, we call it gravitational lensing. Again, creative with names. Now, telescopes on Earth are pretty small by space standards. A backyard telescope like mine will be a few inches, maybe up to a foot or so. Our big fancy new space telescope, its mirror is going to be about 20 feet or a few meters across. And the biggest telescopes we're building on the ground right now, it's easier to build a big mirror on the ground than put it on a rocket and fly it into space, are about 100 feet or about 30 meters. This particular one, which is currently in the planning construction stages, is called the 30-meter telescope. I will leave it to you to figure out why it was called that. If we're using a galaxy cluster out in space as our lens, though, well, that's one followed by a lot of zeros across, and incomprehensibly large number of distance across, to the point where even trying to remember what the actual name for that number is really isn't worth it, because it's not going to mean anything to you. But we can look at these massive galaxies and we can see that this process actually works. So this is a picture of one of these gravitational lenses. The fuzzy yellow stuff in the middle is one of these really big, massive galaxies that we're using as a lens. And if you look around that, you can see these kind of stretched out, smeary looking things. And what these are background galaxies that have been magnified and brightened by the gravity of this foreground galaxy. And these appear much brighter, and they're much easier to see than they would be if we didn't have this gravitational lens in the way. And we have many, many of these massive nearby galaxies to use as lenses. This is a very popular way to see further back into the history of the universe. Now, compared to just point our telescope wherever we want and stare for a really long time, it has a couple of disadvantages. We don't get to precision manufacture the lens. We just have to kind of take a pre-existing galaxy. That's why things look like, smeared out streaks instead of nice, sharp images. We also have to kind of get lucky, because we don't get to pick where these things are. We have to have a faint galaxy we want to see that just happens to be right behind the thing we're looking at. But this does enable us to look very far. Again, with Hubble, we are also getting pictures of galaxies in this kind of reionization era just after cosmic dawn. And with longer surveys, with things like the James Webb Telescope, we'll be able to see even farther, potentially as far as cosmic dawn itself. So these gravitational lenses are kind of a new way of using space itself as a telescope that's letting us see even further into the past. What else can we do, though? If we don't want to, spend a huge amount of money to maybe see one little smudge, and we don't want to have to get lucky and have something, lined up exactly the way we want it to be, we can use a different trick. And this is a trick that's near and dear to my heart. It's what I did my PhD on and what I spend most of my time working on right now. It's a trick where we try to see all of the cosmic dawn galaxies at the same time. And so, in these Hubble measurements, you stare for a really long time and you try and identify the exact little blob of light that is coming from a single group of really faint, really far away stars. And if you want to find another blob of light, you'll have to stare in another direction for a similarly long time and hope there happens to be a galaxy right there. This gets expensive very fast. If I say every dot in this picture is a cosmic dawn era galaxy, I will have to spend a ridiculous amount of time staring at this patch of sky to find all of them. These space telescopes are very popular. There's a lot of people competing for the time on them, time that could be used to look for life on other planets and other things like that people seem to care about. And even then, only some of those little blobs are going to be bright enough to see individually. So maybe you'll see the points I have marked in red, but you'll miss all of the stars that are in these fainter gray galaxies. Even this little red smudge here, even that is way brighter than we actually thought galaxies could be at this point in history. It actually broke a lot of the theories of how the early universe works to have a galaxy this big that soon. So our idea, instead of saying, I don't necessarily, it's really hard to see one of these galaxies individually. I just kind of want to see all of the stars at once. And what you do is, instead of, using Hubble or James Webb to kind of take a super HD picture of a tiny bit of space, you just kind of make a nice low resolution map of a large area of space all at the same time. And that gives you something like this orange blobby mess you see over here. Now, at first, this doesn't really look like anything, but if you look closely, you see that the kind of shapes of where this picture is bright line up with the places where there are cosmic dawn galaxies, where there are stars being born in the early universe. And what this means is that, every bright orange blob here is measuring the total light from all of the galaxies in that part of the sky. And it's a lot easier to see the total light from a bunch of galaxies than it is to see any one individually. And we can do some, if I do say so myself, rather clever statistics on it to see even farther. And what this means is that we can, learn about these population 3 stars, this reionization era, this period in the very early universe, without having to spend tons and tons of time chasing down every single individual group of stars. We can kind of study the whole thing holistically at the same time. And so we are building, there's a lot of groups working on a lot of much cheaper than James Webb telescopes trying to do this intensity mapping idea. 2 that happen to be near and dear to my heart and have a lot of people at the University of Toronto working on them are the COMAP telescope, which is currently running out in the desert in California, and the CCAP Prime telescope, which is under construction on a mountain in Chile in South America. So like with the current Hubble type measurements, these are primarily going to see into the later reionization period of this cosmic dawn event. They're not immediately going to be able to push back to the first stars, but as we develop these intensity mapping techniques and get better at them, we think we'll be able to push back and use this trick to see the first stars in their own right, to watch these first stars being born. And if you wondered why I picked these 2, these happen to be ones that I work on. This person here, who's much taller than everybody else, happens to be me. So the last trick I want to talk about, the last kind of new way of thinking about astronomy that we're developing to try and see these first stars, is a little bit weirder than all of the others. And the idea, I've like to call it tuning into radio hydrogen. And of all these tricks so far, at this point, the first three ideas I mentioned are, they might be able to hit the first stars in a few years, but right now they're really getting into this later reionization period. This is the only trick we've found so far that we might actually have seen cosmic dawn. We're not sure yet. There's a lot of debate, but we might have actually seen it using this radio hydrogen technique. Now, what do I mean by that? Well, going back to our hydrogen atom, I told you this talk was going to be talking a lot about hydrogen. I'm not kidding. Hydrogen atoms, while they're floating alone in space, still with their electrons attached, they actually give off a very faint but constant radio signal. On Earth, you don't see it because they, spend too much time bouncing off of other things and turning into water molecules and things. But if you let an atom sit by itself off in space, it will give off this very faint but constant, it'll give off this very faint radio signal. And using basically big radio dishes like you might use to get your TV signal, we can tune the frequency we're listening to with these radio dishes to see this signal from the hydrogen atoms. Just like the radio station you're listening to is like 101.4 FM, that corresponds to a specific frequency of radio wave being spat out at your antenna. Hydrogen atoms give off their waves with a wavelength of 21 centimeters. The distance between one peak and the next peak of the radio wave is 21 centimeters, or a frequency of about 1.5 gigahertz. The wave wiggles about 1.5 billion times per second. And this is a very specific, very easy to isolate frequency. And then, because the universe is expanding, a byproduct of that is, as you move your hydrogen atoms farther and farther away, these waves that we're listening for, these radio waves, get more and more stretched out because the universe is expanded, and it takes the crests of that wave and it pulls them further and further apart. This property, which we call redshift, means that by tuning our radio telescopes to lower and lower frequencies, we can listen, or look for, listen, these metaphors get a little bit different when we're talking about radio astronomy, to hydrogen farther and farther away. And this means that if we set our telescopes to the right frequency, I apologize for any background noise. My cat ate her dinner before we started, and she's playing with the rubber band and is very excited about it. Anyway, universe is expanding. We can tune our radio telescopes to lower and lower frequencies and look farther and further away. And if we tune our telescopes to the correct frequency, we can see hydrogen gas that's floating around right when these first stars were being born. So let's zoom in a little bit on that period on our timeline. Now, the physics that goes into this is very complicated. It has to do with the interaction between the hydrogen gas and the starlight from the new stars, and actually the leftover light from the Big Bang ends up being really important. But if you go through all the physics, what you find is that if we look at a graph of what frequency we tune our hydrogen radio to, which corresponds to how far back in time we're looking, so farther to the left is further back in time, and how loud or how bright that hydrogen signal is, we expect to see a dip, a rather large dip, right at the time when the first stars were being born, right when they dump a bunch of new light into that hydrogen gas for the first time. That has this interaction which causes suddenly absorbs a lot of the this hydrogen radio emission, and produces this kind of characteristic little hole figure. And we can go looking for it. Now, the first two things I talked about use really fancy telescopes like Hubble and James Webb. The intensity mapping idea I talked about, we are using much simpler, cheaper telescopes because we're not trying to actually make HD pictures of the distant universe. For this trick, we're not really trying to take a picture at all. We're just trying to listen out into space and hear how loud the hydrogen is. And so for this, I kind of hesitate to even call it a telescope. You just kind of take a radio antenna and you sit it out in the field somewhere. And there are a bunch of groups trying to do this because stick a radio antenna in a field is a pretty cheap thing to do. And one group, which was kind of the first group to try this, an experiment called EDGES, which sits out in the desert in the middle of nowhere, Australia. Well, a year or two ago, they released their measurement of how loud the hydrogen radio is at the times when we expect the stars to be born, and they see a dip. They see a dip that's pretty close to where we expect it to be. And if they're right, then this is a signature of the first stars being born. It's not quite as photogenic as a Hubble image, but this dip could be created by the light from those stars blasting out into the primordial clouds of hydrogen and lighting them up for the first time. It could literally be a sign of the first light in the universe. Now, there's some reasons for skepticism about this. Despite it being pretty easy to stick a radio antenna in a field, actually understanding what you're seeing is pretty hard. For one thing, we humans like to use radio a lot. The frequencies we're looking at have a lot of broadcast TV in it, and in fact, the FM radio band itself. You might imagine that the broadcast signal to your TV or your radio is a little bit louder than, faint hydrogen gas at the beginning of time. So there's still some debate about whether that is in fact what they're seeing. There's also a small problem that the dip they're seeing is bigger than we thought it was possible to ever actually be, which for complicated reasons might mean that either there were a lot of black holes floating around before cosmic dawn, or we're actually seeing the influence of dark matter itself, which is something else I talk about a little more in my other talk. Generally, it's really exciting to think about black holes or dark matter showing up in our data, but generally people like to play it safe and say, okay, maybe you're actually hearing radio waves bouncing off the Earth's ionosphere rather than hearing the first stars. So this is still a subject of active debate. There are people actively working on this, and a bunch more of these antennas in a field trying to reproduce the same thing. But if it holds up, then this is our first picture of cosmic dawn. This is our first sign of the first stars in the universe appearing and lighting up the night sky. So, like I said at the beginning, cosmic dawn is one of the last really almost completely unexplored frontiers in cosmic history. But we are closing in on being able to see it for the first time. All of these new tricks we're coming up with we are very close to being able to see these first stars with our own electronic eyes. The first stars which lit up the universe for the first time, the stars which burned off the primordial fog so light could shine through as we see it today, the stars that were the grandparents of stars like our sun, that is the source of all life and heat on our planet. And in fact, the stars which were the original source of the heavy elements our planet is made out of that we need for our very existence. And so with all of these fancy new telescopes and all of these fancy, really new ways of doing astronomy, we are very close to seeing these first stars for the first time and seeing the cosmic dawn with our own eyes. So thank you very much, and I will take any questions that showed up in chat.
Okay, wonderful. Thank you very much, Patrick. That was amazing. I thought so, and there were lots of commenters on YouTube saying the same thing. So just a reminder to everyone who's listening that if you have questions for Dr. Breysse, we will take them now. So please feel free to chat them to him in the chat box on YouTube, and I'm going to relay them to him. So let me go back to the list of questions we currently have. There were a number of people who were concerned about your cat. I think you resolved that concern.
Those are happy cat noises, not sad cat noises, I promise.
It's very hard to tell with cats, I think, right?
Yeah, and very strange behavior for a predator. She likes to talk to the thing she's trying to attack, which I don't quite understand, but
it is strange. So there's a very generic question here that I don't know if you can help with, but the question was, where in the Greater Toronto Area is the best place for seeing stars and celestial objects?
In the Greater Toronto Area, there are not a lot of spectacular sites because Toronto has a lot of lights. Good places, I would say, are the best direction to look is out over the lake, because there's, for anybody who's not in Toronto, Toronto's right next to Lake Ontario. And all of the city lights are, if you look out over the lake, all of the city lights are behind you, and it's easiest to see stuff in that direction. If you want really good stargazing, though, since there aren't the population of Canada drops off pretty quickly as you go north. If you just drive some distance north, the stargazing very quickly becomes amazing. I was camping in Algonquin Park this weekend, and it was pretty spectacular. And you can actually Google, if you Google like dark sky map Ontario, you can actually get a really nice map of where the best places to stargaze are.
Great, thank you. So really good question here. Will scientists ever discover what caused the Big Bang? Is there a leading or dominant hypothesis as to what triggered it?
That is a very good question. And I have to give it a slightly unsatisfying answer of maybe. And this is, again, something I'm going to plug my other talk one more time, because I talk a little bit more about it there. We don't really know what the Big Bang is. The term Big Bang is kind of a placeholder. Really, our theories of the universe cover like literally everything in cosmic history except the Big Bang. It's possible that the Big Bang wasn't a continuous event. There are theories where the universe was just expanding continuously, and there was an event that slowed part of it down enough to let it turn into the universe we see today. There's theories where you can model it in ways that, the question of time itself doesn't make sense before the Big Bang. It's like asking what's north of the North Pole. So there are many, many theories, and none of them really have enough evidence to give a straight answer. But we are working very hard on it, and so maybe we will figure it out someday.
Great. So Nafisa says, could you briefly elaborate on using galaxies as a telescope? I couldn't quite get how it's done in practice.
Yeah, so in practice, basically what we do, let me go find that picture again. So what we do is we take, Hubble, for example, and we find the biggest, heaviest cluster of galaxies we can. We take a bunch of pictures of space so we can find nearby galaxies. We pick the biggest galaxies we can see and stare at those really hard. And so this picture, this yellow fuzz in the middle, is one of those nearby massive galaxies that we've chosen to stare at. So that is this, the equivalent of this yellow fuzz right here. And then the mass of that galaxy is strong enough that it takes all of the light from all of the stars behind it and bends that light towards us. So, some of this light from this galaxy might have gone off into space without us ever being able to see it. This lens, the mass of this big old bright galaxy here, is going to take more of that light and bend it towards us so it hits our ordinary telescopes here. And so in practice, what we see is we stare at one of these really big galaxies and we see these kind of like smeared out things behind it. And, these galaxies are kind of universally like vaguely like circular or elliptical-y on the sky. There are a lot of ranges of shapes, but they don't tend to stretch out nearly this far. So if you look at one of these big galaxies and you see these kind of like smeared out arcs, and if you look closely, you can see they kind of make like a circle around the big guy. That is a sign that you are seeing stuff that's behind the big galaxy, that the big galaxy is acting as a lens and focusing more light from these things onto your telescope. Hopefully that made a little more sense.
Okay, wonderful. Yeah, so Nafisa, if you still have another question about that, please feel free to chat it. But hopefully that helped clarify things. So Jason asks, I heard somewhere that radio static is the sound of space. Is this true, or did I hear this wrong?
That is actually some radio static is the sound of space. And I think I usually heard this TV static, but I guess people use less antennas on their TVs these days. So I mentioned briefly in a couple of places that the light from the Big Bang still hangs around afterwards. It gets fainter very quickly to the point where it's basically radio waves right now. But that light is still hanging around. And if you take a telescope and look even further beyond cosmic dawn, you can see that light glowing as a surface we call the cosmic microwave background. And some fraction of the telescope of the static in your old TV is those radio waves, which were originally the light from the Big Bang. And the interaction of those radio waves with the hydrogen is part of what makes good grief, I have too many slides. Part of what makes this graph so complicated looking.
Okay, great. Thank you. So Alexi asks, is it possible in theory to see the residual light from the Big Bang?
Yeah, and so that's, I guess, covered a little bit by what I just said. We can and have, in fact, actually seen the residual light from the Big Bang. It's a big part of why we know how old the universe is. And even though it's coming from farther away than the first stars, because actually an expanding universe, the light from the Big Bang is coming from, the Big Bang itself. It's older and therefore we have to look farther away. The Big Bang is so bright that we can see it even though we can't see the first stars themselves. And there's a lot of people at Toronto working on experiments to do that, actually. There was one called ACT, which just released some really nice new maps of that light this past week. ACT, if you want to look it up and learn more.
Indeed, and we have some other talks in the series where people talk about their work on that first light of the Big Bang.
Oh, good.
So another really interesting question. So this is going back to gravitational lensing, and it's just a point of clarification. So why are there stars or galaxies or whatever visible around the galaxy that's being used as a gravitational lens, which don't themselves look distorted?
Yeah, and so the reason for that is, so this is actually part of why I picked this particular picture, is that this is actually a pretty good like three-dimensional picture of what's going on. Most of the yellow stuff and the undistorted yellow stuff in this picture is galaxies that are about the same distance away as the big one. In fact, an awful lot of them are actually orbiting around the big one. And so since they're not coming from behind it, their light doesn't get bent nearly as much. And some of these things, like this probably, are actually just stars in our own galaxy that are on cosmic scales basically right next door. And they just happen to be in the same picture. It's actually a major challenge in astronomy. You take a picture like this, trying to figure out what things are really far away, what things are close by, and figure out what's interacting with what. But yeah, anything that's not smeared out is just either at the same place as that big galaxy or between it and us. And so it doesn't feel the big galaxy's gravity.
Yes, I think that's one of the difficult things to understand often when looking at, astronomical images that look deep, deep, deep into the universe, is that you're not just seeing the thing you're trying to look at, you're seeing everything that's in the direction of the thing you're trying to look at. It's sort of like trying to, photograph a fish at the bottom of a lake or something. You're seeing all the other stuff that's suspended in the water column between you and that fish. And it can be difficult to disentangle what's what.
Well, I'm going to steal that metaphor.
Yeah. So Mary has another question about the very early universe. Is the light from the Big Bang also from the fusion of hydrogen into helium?
It is actually not. Going along with we don't know exactly what caused the Big Bang. We don't know exactly what the light from the Big Bang is sourced by. But what we think it is that in the very beginning of the universe, it was getting bigger extremely quickly, like ludicrously faster than it is now. And through some process we don't really understand, all of that energy from that expansion, all that rapid expansion, got turned into heat. And if you have stuff that's very hot, like metal out of a forge, it glows. And so the light we're actually seeing is the glow of the original particles in the universe, glowing under the heat that's left over from the Big Bang. And actually, it's not related to fusion, but the reason why we see it where we do is this point called recombination, is actually the point where the universe cools off enough that electrons and protons can stick together for the first time and make atoms. So actually, when we look at this cosmic microwave background, this light from the Big Bang, what we're actually seeing is the very beginning of the Dark Ages. And right now we're looking for the end of it.
Okay, thank you so much. So I think that's the last of the questions coming in from YouTube. So I'd like to thank you again. And there were very many people thanking you in the comments, people saying that this was a really wonderful talk. So I'd just like to remind everybody that if you have an interest in following up a little bit and learning more about Dr. Breysse's research and his interests, you can refer to his other Cosmos from Your Couch talk, which is linked in the description box below. And if you have more questions, please join us again next week at the same time when we're going to be having an open question and answer session with a panel of astronomers who will try and field all of your questions that they possibly can within the space of an hour. So get those questions ready. And just a quick plug, if you haven't done so already and you're interested in doing it and you're viewing from, mostly within North America, then try and go out tonight and have a look for Comet Neowise, which is a really spectacular sight. You'll be able to see if you look in the northwest tonight. If you know where the Big Dipper is, look around the Big Dipper with some binoculars. You should be able to see Comet Neowise. And there's lots of instructions you can find online to help you find it, but it's worth seeing because you won't have another chance for about 7,000 years. So thank you again very much, Dr. Breysse, and we'll wrap for now, and we'll see everyone next week.
All right. Thanks a lot, everybody. And thank you very much, Mike.
No problem. Okay, so our